This is Motion in One Dimension continued. In this video, we're going to cover average velocity from a graph, average acceleration from a graph, instantaneous velocity, and speed. Just like last year, motion can be represented by graphs, like something you saw when we did the constant velocity lab. On the x-axis, we're going to have time, and remember that it is the independent variable. Time will go on whether you want it to or not. On the y-axis, we have the dependent variable. In this case, it is position. Different ways that you can see these graphs labeled as are position versus time, distance versus time, or displacement versus time. All these three things mean the exact same thing. So remember that average velocity is our displacement over time. Remember that we are looking at displacement, not total distance traveled. Total distance traveled over time would have given us average speed. So if we were looking at a graph, then we can say our displacement over time would be the slope of the graph. In this case, it happens to just be the slope at any point on this graph, because we can see that the speed at one point is a speed all the way through. This example is a little different from the previous one. Here you see that something's happening in between point A and point B. But if you're looking for average velocity, it doesn't really matter what's happening in between these 2 points. All you care about is your final position and your initial position. So it would still be the slope of the line between these 2 points. So to give you a slightly better visual, I went ahead and labeled these 2 points. So point A is labeled the coordinates as the time at A and the position at A, and then the B's coordinates are the time at B and the position at B. Again, I know that B is our final because it comes later in time, and I know that A is initial because it comes earlier in time. So if I want to solve for the average, I would do the position at B minus the position at A divided by the time at B minus the time at A. So, for an example, from the graph, determine the average velocity for the particle as it moves from point A to point B. Again, all we're concerned about is your final position and your initial position, and the time it takes to travel between the 2 points. So, this is simply the slope of the line between the 2 points. Final position at B is -1 meters. Initial position at A is 0 meters. Final time at B is 0.5 seconds. Initial time at A is 0 seconds. So you get -2 meters per second. Now, this example is asking for you to determine the average speed as it goes from A to B. Now, for average speed, we are looking at a slightly different equation. We are concerned with the total time it takes instead of the displacement. So here, we need to do something slightly different. First off, we need to solve for the total distance traveled. So, from here to about here, we traveled about 1.8 meters. You can go ahead and say 1.9 also, that's okay too. From here to here, we traveled another 1.8 meters. And from here to here, we traveled 1 meter. Yes, it is in the negative direction, but for speed, we're only concerned about positives, because it is a scalar. Putting it all together, our average speed is distance over time, which is 1.8 meters plus 1.8 meters plus 1 divided by 0.5 seconds, the total time it takes to travel from point A to point B, giving us 9.2 meters per second. We now know that the average velocity between 2 points is the slope of the straight line connecting those 2 points. So what if we brought those 2 points closer and closer together? Until they're practically the same point. This is known as a tangent line to the curve. The slope of this line is known as the velocity or instantaneous velocity at that point. Remember, because we were talking about velocity, it is still being considered a vector. But when we start talking about instantaneous speed and it being a scalar, this one, you can just get the absolute value of your instantaneous velocity. So sometimes in problems, you'll see it ask for the speed or velocity at a certain point. They're referring to the instantaneous speed or the instantaneous velocity at that point. So basically, tangent lines that represent velocity of position versus time graphs help us understand position versus time graphs a lot quicker. So here, I can draw a tangent line to the curve at that point, and I can look at the slope of that line. I know the slope is equal to 0. If the slope is equal to 0, then the velocity is equal to 0. Then I can draw a tangent line over here. Look at the slope of that line, which I can see is a negative slope. Meaning I have a negative velocity at this point. Same thing here. 0 slope, 0 velocity. Positive slope, positive velocity. Again here, 0 slope, 0 velocity. So for these kinds of graphs where we have exactly straight lines, it's really helpful to see them very quickly and very easily. But when we have curves, such as in this example, you can look at a tangent line at each individual little piece and see what's happening to the velocity as it changes. So, for the first part, I can draw a tangent line here, meaning that I can see it's starting from a 0 slope or 0 velocity. Here I can see that my slope has slightly increased in the positive direction. And then over here, I can see that my slope has increased even more and it's still in the positive direction. So if I go from a velocity being equal to 0, slightly increased slope, and an even larger increase in slope later, that means I am getting faster. You can try the same thing with this example. I have a very steep slope here. A not so steep slope here. So this one is still in the positive direction, but it's slightly smaller than it was a previous time segment earlier. And now we can see that we get a flat line, meaning a velocity of 0 later on in time. So if we see this kind of progression, we can see that our object is slowing down, to a stop, in fact. From the graph, determine the instantaneous speed and instantaneous velocity for the particle at point B. So we are looking at a specific moment in time. So I start off by creating a line tangent to the curve at that point. Then I find the slope of that line at that point. For this particular case, I'm going to go ahead and estimate my coordinates I'm going to be using. So I'll go ahead and use this one since I can see a point. And this one's actually fine. So the points I'm going to use are 0.4 seconds, 1 meter, and 0.55 seconds at -2 meters. So the slope of that line would be -2 meters minus 1 meter divided by 0.55 seconds minus 0.4 seconds. So this is the velocity at B. You should have gotten -20 meters per second for your instantaneous speed at point B. Instantaneous velocity. And for your instantaneous speed, it's simply the absolute value of your instantaneous velocity. So 20 meters per second. So this entire time we've been talking about speed and velocity, but remember that we can also talk about average acceleration. So our average acceleration is our change in velocity divided by our change in time. So, and remember that we are talking about a vector here. So final velocity minus initial velocity over final time minus initial time. It takes a motorist 1 minute to change his speed from 20 meters per second to 30 meters per second. What is his average acceleration? If we're solving for average acceleration, we need to know his final and initial velocity. So final and initial velocity. And the time it takes to complete it. Because we are working in meters per second, we need to make sure that we are working in seconds. Go ahead and try this example. Your final answer should have been 0.17 meters per second squared. To get this, we simply get the change in velocity over our change in time. So final velocity minus initial velocity, in this case, it is 30 meters per second minus 20 meters per second divided by the time it takes to change, 60 seconds. You should have gotten 0.17 meters per second squared. Always double checking your units. So everything that we did to position versus time graphs, we can also do to velocity versus time graphs. Remember that time is your independent variable, velocity is your dependent variable. Another way you can see these graphs labeled as velocity versus time or speed versus time. Here I'm only showing the first quadrant, but remember that all of these can actually go into the negative. So we can also have negative velocity, because right now we're only showing positive. Same thing went for position versus time graphs. So for the slope of a velocity versus time graph, again, we look at our units. If we have meters over seconds, then we have meters per second squared, which means acceleration. So again, for the slope of a velocity time graph, we get acceleration. Mostly the examples that we're going to see are going to be constant acceleration. Again, anything that we did to position versus time graphs, we can also do to velocity versus time graphs. So when we start talking about tangent lines, we can also do that to a velocity time graph. So here, if I draw a tangent line here, I want to look at the slope. Here I have a positive slope, so that means I'm going to have a positive acceleration. Now for these, we need to be extra careful. That doesn't necessarily mean that we are speeding up. And we'll talk about this a little bit more in class. Here, I have zero slope. That means zero acceleration. That doesn't mean that we are not moving. We can be moving, but we just have no acceleration. We're not speeding up or slowing down. And here. Here we have a negative acceleration because we had a negative slope. Again, we can't always assume just because we have a negative acceleration means that we are slowing down. That's not always true.